This video is part of a course on food physics. The single phase transport equations is one of the frameworks for modeling or understanding food physics. It is part of the theory section. And this video is a summary of the entire single phase transport equations. So here I'm making a few summary comments, including how this module fits in the overall scheme of things. And I've divided into three parts just for convenience. So first, a summary of the equations. So in this course or this module, we derived equations for heat transfer, mass transfer, and fluid flow in only one phase. So here we show the simplest form of the equations, still with all of the terms, but in 1D, so we can relate to the physics more easily. We can see it more easily. The equations here are all statements of some of the most fundamental principles in science. So this one is conservation of energy, this one is conservation of mass, and this one is just Newton's laws of motion applied to fluids, or conservation of momentum. So each of these equations has multiple terms representing different physics. So for example, the first term in the heat equation, this first term has to do with energy storage. So if temperature changes with time, that means if it increases with time, it stores more energy. If it reduces with time, it stores less energy. So the first one has to do with storage. The second term has to do with how energy is carried. So notice the velocity u. So it has to do with how energy is simply carried due to bulk flow. And the third term has to do with how heat conducts. So here is the thermal conductivity to remind us. And so this term has to do with how heat is conducting, and finally the last term has to do with conversion of other forms of energy into heat, like in microwave heating of food. For the heat equation, it is as if energy suddenly appears. So energy suddenly appears. So it is also called a heat source term. So it's like a source of heat, but it's really conversion from some other form of energy. Completely analogous terms are there for the mass transfer equation, this one. And so let's see those equations. So then again, you have the first term that represents storage of a mass species. The second term has to do with mass transport due to bulk flow. The third term has to do with diffusion. This one has to do with diffusion. We can take this guy out. If diffusivity is constant, then we'll see this also has the second derivative like the heat equation. Then the last term has to do with, just like heat source, it's a mass source where mass appears. So how would mass appear? It is typically from a chemical reaction that something is produced or something is depleted. It can simply be let's say, formation of vapor. If I am doing this equation for a vapor phase and liquid water changes to vapor, then we have a mass source. The momentum equation, which is really Newton's laws of motion, while analogous, has to be physically interpreted, I feel, a little differently. The first term is acceleration. So you can see its derivative, time derivative of velocity, change in velocity with time. The second one is when fluid moves into it's also due to acceleration, but it's when fluid moves into a domain of higher or lower velocity. And the first one on the right hand side, that's this one, and really the entire right hand side is composed of different forces. So the first one is force due to pressure. The second one is the force felt due to viscosity, and the third one due to body forces like gravity. A much more general version of these equations in various coordinates and full form of each term can be seen in pretty much any standard transport phenomena textbook, so I'm not repeating those here. Item number 2 in this summary. Okay, so what do we do with these equations? How are they useful? And so they are used to develop mathematical models to understand and optimize food processes. And this modeling process in a nutshell goes like this. We start from a physical situation like this deep frying process, and then we look at this more simplified schematic of it, decide on the geometry and so on, and then we bring in the physics through governing equations and boundary conditions, and then finally we solve these equations to understand better of the physical situation. And where the chapter and the equations fit are here. So the equations that we derived are the governing equations for the particular physics. So when we need those governing equations for a particular physics, we have choices. So we can think of almost a lumped parameter, or the one we just did, which is the single phase equations, or we can go to progressively more complex. And so I want you to see we are here. The equations we derived are at this level. They are certainly more complex and describe a lot more physics than this guy, lumped parameter, which is very simple, where the entire material is considered at one temperature or one moisture. So this has a lot more physics and very different beast altogether. But if we want even more details of a complex food process like this one, bread baking and so on, then of course these single phase equations that we just described or in this chapter is not enough. We need to go for more complex or multi-phase porous media framework that is described in our follow-up module or course. So this is extremely good and still can be improved in more complex and multi-phase porous media models. Likewise, we need boundary conditions for the equations to complete the description of the problem. We need to know how many boundary conditions and what type. Is it temperature given or flux given or convection? We need to know those. And so that's where this chapter with the governing equations and boundary conditions fits in the big picture of food physics and modeling. And this is just to repeat the three types of boundary conditions that we have talked about. One is value given, like the value of temperature or concentration. Another type is flux given, of temperature of heat flux or mass flux, or this convection. Now there can be combinations and other complications, but these are the most basic types of boundary conditions that we use. Now the third or the last item. The single phase equations, that is for this chapter, stand in terms of their applicability to food. Now if you take something really simple like a almost a pure liquid food, of course it would be more directly and obviously applicable. You can even extend to some simple solid heating situations where there's not much complication. But the equations that we derived here are the most widely used. They're the most used equations in food, so they actually apply to more complex situations. So let's pick this one. Let's say for meat, meat has the solids and liquid water, water vapor, fat, and so on. So many different phases. So how the equation is used in these kinds of complex systems, whether it's the potato or the rice grain or the fish or the sausage, all of these, eh, it is the phases are averaged carefully and in different ways, but phases are averaged, and then the equation actually looks like very similar or the same as the single phase equation. So this is how it is extended. The single phase equations are extended. Another way it is extended to many real world processes is to use equation for each phase, a separate equation for each phase simultaneously. So let's say we are trying to model drying inside this dryer. So we'll have one equation for the air and one equation for the solid phase. And the equation for solid phase in turn could be a composite like average, the kind we just talked about. So in this case, then, separate single phase equations are used or can be used for fluid and solid phases. So again, for example, these water and peas inside the can. So there will be one equation for water, one equation for the peas. So this is how these equations are extended to a much more broader applicable situations, and they're extremely useful in understanding food physics. So one way to see this is the single phase equations can be building blocks. You can think of them as building blocks for more complex models. So here's an example of how we can model bread as a porous medium to understand or model bread baking, let's say, but it is based on or starting from those single phase equations. So we write the single phase equation, for example, for water, for vapor, for air. And then for temperature, we know there'll be heat conduction in the solid, in water, in vapor, and air. And instead of writing separate equations for all of those phases, we say they all share the same temperature, so we'll write one averaged equation. And this averaged equation very much looks like the single phase equation that we derived, except with averaged properties. And then for mass transport, we do have the equations that are even closer to what we just derived. So very complex multi-phase porous media systems can be based on those single phase system equations that we had, or at least understanding these more complex systems, it is helped much by the equations that we just derived. So then pictorially, of all these many levels of modeling possible, we did this one, that is a single phase equations that are more complex than the lumped parameter one, but are or can be seen as building blocks for more complex porous media model, which are the next set of modules or courses in this sequence.